Hey everybody, it's Dr. J, and today we are talking about strong acids and strong bases. Now, key thing we want to understand first about strong acids is that strong acids are going to completely dissociate in water. Period. That's it. All right, it's going to completely dissociate. Now, when we're thinking about strong acids, let's think of a strong acid, hydrochloric acid, right? Very strong acid, high Ka value, etc. All that. When it goes to dissociate, it's completely dissociating into the ions. What we see here is that it dissociates and gives me my H plus, right? One of the key factors of an acid, as well as it's going to give me my conjugate base. Now, please, everybody remember, your conjugate base is basically the thing without the proton. All right, in this case, we got HCl, it dissociates, so it's the thing without the proton, right? So this is our conjugate base. Now, here's a little side bit. Acid strength is defined by your conjugate base, all right? This is how we know, right, if you're going to have a weak or strong acid. In this case, chlorine just by itself is a very, extremely weak conjugate base. Now, because we have this extremely weak conjugate base, right? Therefore, we're going to have a very strong acid. Okay, so this is just a side note. You know, your conjugate base defines your acid strength. As well as how can we read that acid strength? Well, we can read it by knowing the Ka. And as we mentioned before, Ka, equilibrium, products of reactants, we're going to get a very high value. If you got a very high value, in this case, it's greater than 1. Okay, but if it's a high value, like 10.8, that means that you're probably going to have a strong acid. All right. You're probably going to have a strong acid. Now, here's some common strong acids that are going to be helpful for you guys. Anything that has a hydrogen and a halogen, yo, it's probably a strong acid. Hydrochloric acid, hydrobromic acid, right? Anything of the sorts, probably going to be a strong acid. Sulfuric acid, another one, nitric acid, perchloric acid, all of these are common strong acids. And then our mineral acids are also strong acids. So HCl, H2, SO4, HNO3, like I mentioned before, but they can be referred to as mineral acids. Okay, so these are the common strong acids that you probably should know just off the top of your head. That it'll make it easier long term. But yeah, these are your common strong acids. All right, everybody, I'm down here. Real quick mind break. Okay. Before I get to strong bases, here's one thing we got to think about with pH. Okay. So with pH, right, for example, let's say we got a solution that is a pH of 5. Okay. Now, when we think of pH of 5, we're probably going to be thinking in our head, oh, okay, it's not a 1 or 2, so it's probably a weak acid. No. Okay, well, I won't say no. It could be that. All right, it may be. But when we're talking about pH, we're talking about the overall solution. Okay. So when you hear me say pH of 5, we're talking about a weakly acidic solution, not a weak acid. Okay, that does not mean it's a weak acid. It's a weakly acidic solution. So, right, a weakly, a weakly, man, these words, y'all. All right, so a weakly acidic solution, right, could mean a couple different things. We could have a weak acid. That's very much true. Or we could have a very small amount of a strong acid, right? We really don't know. We don't know until you ask somebody. Okay. So that's what we have to think about with pH, right? It can be composed of either a weak acid or a very small amount of a strong acid because we understand, right, that pH is the solution, not necessarily the acid or pOH or the base in the same instance, okay? So we want to understand that, okay, when we're going forward. Be careful with your language. Now let's go on to strong bases. Okay, strong bases. All right, so here's a huge hint. Strong bases are usually going to be alkali metal hydroxides. All right, they're usually those. Now, a strong base, just to remind everybody, in this case, they're going to completely dissociate, just like with the strong acids. That's how we know something's strong. It's completely dissociating. Okay, and just like with strong acids, in this case, they completely dissociate. But guess what's the difference here? Right? In this case, we got a weak conjugate acid, in this case being sodium, this sodium plus. So if we look at sodium hydroxide, a very strong acid, it dissociates into sodium ion and OH, right, hydroxide group. Now, this is a weak conjugate acid, and because it's a weak conjugate acid, this is a strong base. Very, very similar, the same concept as we mentioned with our strong acids. And then if we look at our KB, so in this case, notice, right, we're not saying Ka for acids, we're saying Kb for bases. So whenever we're talking about equilibrium, please make sure that you're using the right Ka, Kb, Kw, whatever. You understand what you're using. So since we're talking about bases, it's Kb. But it's still the same. It's going to be still set up the same way. Products over reactants, right? We got our products, we got our reactants, right? And then in this case, we're going to get a very high Kb value. You got a very high Kb value, you got a very, very strong base, okay? So some common strong bases that you guys should definitely know is basically those alkali metal hydroxide groups. So basically that's like lithium hydroxide, sodium hydroxide, potassium hydroxide, right? We could go on that whole group of alkali metals, okay? As well as alkaline earth metals can be medium to strong bases as well, right? Calcium hydroxide, strontium hydroxide, and etc. Now, in that group, however, the very top two elements in that group of alkaline earth metal, we are not going to consider beryllium or magnesium to be strong acids. They're actually, so beryllium or magnesium, those top two in alkaline earth metals, they're actually going to be weak bases in this case, all right? So they are actually partially dissociating in water, as well as beryllium and magnesium cations actually have a smaller ionic radius. Okay, so that's going to impact when we're talking about coordination with the water. Okay, so it is that type of play. Okay, but basically, just know beryllium and magnesium weak bases, but everything else, so it's going to be probably a strong base. And this is very important to remember, everybody. Um, if you are given an OH concentration, you are able to convert that to pH. So we would basically convert our OH to H plus by using this equation, right? That Kw equation to just solve for our H plus concentration. Kw is always going to be 1 times 10 to the negative 14 over whatever OH concentration. And then we have our H plus, and then we can just use our, negative log to give us to our pH. You could also do this by converting your OH to POH, right? We know how to do that, negative log. And then, right, convert our POH to pH. In this case, we're just going to do 14 minus POH. Two different ways to get us from OH concentration to pH.